Hello, hello my friends, this is for Planes, and welcome back to Kerbal Space Program. Today I'm going to be holding a nuFAR tutorial. nuFAR, Ferrum 4's upgrade to the new stock Aerodynamics, and has changed quite a lot of things. Notably, you might see I'm flying at around 950 meters, 1000 meters a second, at Mach 3.25, which is something 3.28, which is something Ferrum 4 provides. I'm chugging along nicely on the planet, which is something on the stock aerodynamics is extremely difficult. I'm using a singular jet engine. It says 22 kilonewtons of thrust, which would be quite madness if I used the stock aero for it. If I did that in the stock aero, because the stock aero has a way higher drag than this. This is my impression, as you can see. Well, you can't see the name. I would dearly like to. Of a MiG-15 Biz, although I did give it the J-79 Starfighter engine. So yeah, it's a hybrid thing. I tried to replicate a MiG-15 Biz as well as I could. This was the closest I could get, while making it work with FAR. You can see I have an indicated range of about 6,000 kilometers, which is enough to fly me around Kerbal once. I'm flying in the opposite direction, as you can see. So, what's new in nuFAR? Nice of you to ask, I guess. We'll land this aircraft. Now fast forward that with some music and bit of editing. And yeah, I'll see you guys in the space plan hangar. No, I won't be seeing you guys in the space plan hangar because I have a few things to talk about. First thing is these here. You can see when I roll it, you turn it on, and it stabilizes you in the airstream. Quite useful, I'd say. I lost my train of thought. Yeah. These stability indicators. The yaw thing is something I leave on default, so when I do yaw out of the airstream, it tends to catch myself a lot quicker. Even though it's mostly non-useful, these here I don't use because I'm flying with a stick. This is a dynamic pressure control regulation, which is quite useful if you're flying mouse and keyboard. And as you see, our drag is quite low. We're still not really losing speed, though I'm pulling quite a bit. And I'm being very careful not to go over about 9 Gs, because I could lose my wings, which is also a feature of FAR. We're going to drop below, we have dropped below sonic speed, as of yet. Oops. And that makes my aircraft a lot more responsive. As you saw, I pulled 15.5 Gs. Not very healthy for the airframe. I would say FAR is mostly to be enjoyed with flying with a joystick. That is how I would say you should fly in FAR. And we've estimated our landing spot quite a bit. Yeah. It's a whole lot less smooth than I anticipated it to be. So yeah, help to demonstrate a few features. Air brakes do work in nuFAR. You can see, this thing started slowing down majorly quickly once I deployed the air brakes. I'll see you back in the hangar. I did end up reverting back to the hangar because it was too much of a hassle to land it, and I don't have all day to do stuff. And I'll walk you through the features of FAR, which are as follows. You have a static stability analysis tab that provides you with a bunch of information. These graphs are fairly important, and you should take your time learning how to read and interpret them. This button here currently sweeps your angle of attack at a certain speed, indicated right here, Mach 0.5, and returns a bunch of graphs for you to take a look at. These graphs are the green lift to drag coefficient. Basically determines how efficient your aircraft is flying at a certain angle of attack. This one here indicates my most efficient angle of attack is about 6 to 7 degrees at Mach 0.5. This blue line here, which is your lift coefficient, topping off at about 22 degrees angle of attack, which it then goes into stall profile. This red line here, my drag coefficient, rising up to about 20 some degrees and then going up a bit higher when we're stalling. And I'll extend the graph a bit by putting in a higher upper limit with a wee bit more points, so to be more precise. You can see the drag goes really high once we are at a very high angle of attack. And you can see, yeah, and you can, one of the most important lines I would say is the yellow line, this here. These are fairly, provide some useful information. This one here is the most important. This one is your stability line. This here is a representation of the torque that the airflow puts on your airframe at a certain angle of attack. If it is below the 0 line, the torque always rides your aircraft into the airstream. If it's above, it rides it away from the airstream. So this, you want it to be below 0. Always. Slightly, but not too much. So about like this here, this part. More or less. The closer it is to 0, the more pitch responsive your aircraft is. You can also go into negative angle of attacks by putting a negative indicator here. And you'll see, because it's not stalling out in the negatives, this is a fairly predictable pitch attitude until I start stalling. You can also sweep across a Mach speed, which is something I usually don't do, from a certain lower Mach speed to a certain upper Mach speed with a number of points at a certain angle of attack. I usually don't do that because it's not very indicative. What I usually do is I change the speed here. So this is a representation of my supersonic aircraft behavior. And you will see that quite some lines here change. Mostly the blue line, which means that in supersonic conditions, or here in supersonic flying conditions, you will see that you don't really start stalling up to very high angles of attack. And what also very often can happen is that when you're going very quickly, this line here goes a lot flatter, which means, or which is like your aircraft becoming unstable. What is also interesting is that my aircraft has my lift indicator becomes 0, my lift coefficient, at a negative angle of attack. So that's something to keep in mind. So these are some fairly interesting bits and pieces of information. Read these graphs, interpret them. It'll give you a very good overview over your aircraft's performance at specific speeds. The upper hard cap is 90 degrees on this, and it's basically what happens if you're pancaking into the airstream. And quite possibly is a very interesting way of showing it to your aircraft what you should do. You can see we start stalling at about 45 degrees angle of attack. at Mach 5. So this is a useful feature for designing crafts around re-entry speeds and taking a look at how they perform at certain speeds. You can change your pitch here from -1 to 1 to indicate, like, to make your pitch adjust and simulate with a input pitch, and you see that my aircraft here does also change its shape depending on what kind of value I put in here. And it'll tell you, this knot here will tell you what kind of angle of attack you will have. You can basically take a look at the specific values and stuff. For re-entry, you probably are going to want to have a very high AOA, but you have to be careful so that your aircraft is still stable. Not just on the pitch, but also on the yaw axis here. So that might require some shenanigans and high dihedral angle wings. Words today. Let's reset this to normal values. Another feature this provides, if I had any flaps on here, is to simulate with input flaps. So if I activate these here as flaps, just for that, and I want to know what I have within, like with landing flaps, what kind of angle of attack, I could do that. Although I should probably not do that, make these flaps, because it would be rather stupid of me. Okay, so we have taken a look at the static analysis. If you have clicked on data and stability derivatives and want to know what this is about, click on the annotation or like go back a couple of minutes and you'll see that. Data and stability derivatives is something I don't really visit very often, so I don't really know a lot about. But what I use it for is to calculate what kind of speed my aircraft would take off from the runway, which is the level flight here. So you click on data and stability derivatives and it tells me at 85 meters per second my angle of attack is 6.8 degrees. With inactive flaps? Yeah, 6.8 degrees. So that means if my gear is out, I can probably take off at 85 meters a second, because that's more than 6.8 degrees of an angle to the runway. Very useful feature. You can more like tell at which airspeed you could probably take off. So this one could take probably off a... Nope, Mach 0.2 is not the correct one. 0.21. 0.22. Yeah, probably at 0.22. So, awesome feature here. That one here is something I don't really know what to do. Or, I forgot something about data and stability derivatives. These are your aircraft properties. You have your wing area, your... a lot of things, scales, chord and span and stuff, and products of inertia, moments and stuff. But what's really important is that you don't have any red things here, because these are your pitch derivatives, and if they go red, or your yaw and stuff, then you're basically doomed. You could of course put in an altitude, a Mach number, and let it calculate. That tab here is something I really don't know what it does, but I can probably guess. But yeah. Then we have a new tab in here they call the transonic design. That is a very important tab for the normal Kerbal Space Program user to be using with the new FAR. Because this value here, to a large extent, and this value here to a smaller extent specifically govern supersonic drag. So if you do want to fly faster than, say, Mach 0.8, you really should take good care to keep your Mach 1 wave drag area low, and your max cross-section area somewhat low as well, but especially the Mach 1 wave drag area, because that can get fairly ridiculously big if you're not paying attention. And that has to do something with cross-section area distribution, which this tool helps you with. And for the main purposes, I shall hide my gear, take it in, which FAR provides a very friendly button for. You can see it goes down from 2.2 meters squared to half a square meter. The transonic thing. And this is how my transonic area looks. There is a fair few bits and pieces that goes into what makes a low drag supersonic aircraft. One of them is the yellow line. You're gonna wanna have that rather low, but that's not the entire thing. The very important factor is the cross-section area distribution. As you can see, this goes up here and goes down. I've tried to get as close as I can to a Sears-Haag body distribution of cross-section area, which is something I should probably demonstrate by creating a Sears-Haag body. Alright, I found a better substitute. I just had to change the nose cones. Stupid as this may seem. And we ended up with this kind of a thing. As you can see, the cross-section area goes up rather high, stays more or less the same, and goes down at the end. You should maybe take a look at Sears-Haag body in Wikipedia or something to read up a bit, because it's fairly interesting. Yeah. But you're gonna wanna have some kind of this distribution, and you're gonna wanna keep this yellow graph rather low at the same time, which can provide itself for quite the challenge. So yeah, let's load our MiG-15 biz. And it loaded it some kind of faulty thing, because it saved it with the gear out. Well, as you can see, I managed to approximate this rather well, and I did need to use some trickery. And for the purposes of this, we shall save this as the demonstration aircraft. What trickery I needed to use, I basically had to place a couple of things on it. For example, as I take these off, you will most likely see that, yeah, as you just saw, our wave drag area goes up from 0.49 to 0.58. Let's hide this. To 0.63, so that didn't really do a lot. But you can see we have some dips in here again. To 0.69, so that really didn't help a lot either. To 1.28. To 1.5. Yeah, you can see this is really not an optimal cross-section area distribution here. So I had to help myself out with placing the air brakes at the right spot, placing some attachments at the right spot. Come on. Thanks for letting this be deleted. Placing the gears at the right spot, and everything that goes in here. But yeah. We essentially have about halved our supersonic drag with this. So I guess this is quite impressive. That one here was a fairly interesting part as well. You can see this has quite the ridiculous Mach 1 wave drag area. Mainly because I didn't really design it correctly. It's very long and thin at the front. It would probably be better to have it short and squat. Yeah. Some of the things I made. Probably also the case because I have the gears out. And it helps a bit, but not a lot. It's because I have the cross-section area distribution wrong. I should probably try taking off some of the cross-section area from here and move it here. This was another design I did, which is quite a lot better, as you can see, than the first design. It's quite a difference. It has half the square, half the cross-section area, but 5% of the Mach 1 wave area drag. And as you can see, I took much better care to design it according to the cross-section area rule. This one here flies very nicely. It is ridiculously heavy. And it achieves orbit around Kerbal with a 30-ton payload. Because yeah, just examples. I could probably use this as a supersonic aircraft as well, but I like transport aircraft. The gear itself is nicely placed. It does lift off the runway quite well. The Flash Turbo Ramjet. Let's build this up. And then we had on this a winglet like this. Put up at 315%. So yeah, this would probably be a very good supersonic cargo aircraft. Right, I nearly forgot to tell about one of the most important features of FAR for me as a plane builder. Yeah, before going into all of these things here. And that would be having the ability to configure my control surface or all my wings as I really want them. And that is very, very powerful. You can see I can configure any control surface to the exact actuation I want from it. So I can say this one here does not move on roll input. It will not move on pitch input. It will only move at yaw input. That's a very, very, very powerful tool. Do not under any circumstances underestimate this. So I guess, guys, thank you very much for watching this FAR tutorial. I have no clue how long this will be. I hope you enjoyed me building aircraft. This is one of my best aircraft I've made yet. It's so low drag that it basically does not slow down. Yeah. I should probably hint, designing my aircraft on the hardest difficulty. You can design at lower difficulties, which means you're not as much bound to the area ruling. You can reconfigure almost any feature like your graph colors, what your default flap, what your default action groups are, like lots of things. What kind of like threshold you want for aerodynamic failures, what atmosphere compositions. You can reconfigure anything, although I leave this stuff stock. As you might have seen, I can do a 9.5 G turn with a fighter. So I guess this is good enough by any stretch of the imagination for me. By this point I should probably say thank you very much for watching. Bye. And you can see the rest of what I recorded to some music. And have to not listen to my rant that I then put on. Bye bye.